A transformer is an electrical device that is used to change the voltage supplied to a higher or lower value. The electrical device that does not work except on AC current needs an AC power supply, which is represented in the animation by the black sphere. The AC source supplies an AC current to the shown coil, which is known as primary coil or the input. This AC current on the primary coil, as we said before, is like any other AC current, and it produces a constantly changing magnetic field. The square-like iron core transfers the changing magnetic field from primary coil to another coil on the other side of the iron core. This is named the secondary coil or the output. When this coil feels the changing magnetic field, an induced AC current is generated in this coil, causing the bulb to light. A basic transformer is made of three parts. The iron core, which in our case has a rectangular shape. Note that it can have many shapes, like a circle for example. On one side of the core there is a coil named the primary coil, and it's the input. On the other side is another coil of different number of turnings, and it's named the secondary coil or the output. We must say here that the secondary coil may have less number of turnings, and in sometimes may have greater number of turnings than the primary. The primary coil is connected to an AC power supply. The output is connected to the consuming parts of the circuit. In our case, it's connected to the bulb. When the primary coil is fed by the AC voltage, this causes a constantly changing magnetic field to be created in the core, which is transferred through the iron core from primary to secondary coil. When the secondary coil feels the changing magnetic field, an induced AC voltage is generated in the secondary coil, causing the bulb to light. If you are of those type of students who like flowcharts, you can understand it this way. An AC voltage is fed to the primary coil. This causes a constantly changing magnetic field in the iron core. The iron core transfers the constantly changing magnetic field from primary to secondary. And now the secondary coil changes the constantly changing magnetic field to an induced current. From another point of view, if we concentrate on the three main parts of the transformer, we can see that we have number 1 primary coil, number 2 iron core, and number 3 the secondary coil. What happens in the primary coil? In the primary coil, the AC current or voltage causes a constantly changing magnetic field. In the iron core, the constantly changing magnetic field is transferred from primary to secondary coil. In the secondary coil, the constantly changing magnetic field that reached the secondary coil causes an induced voltage that is related to the number of turnings. If you take a look at the flowchart of the work of the transformer, you can simply notice something that looks non-understandable. The transformer takes AC voltage on primary and produces AC voltage on secondary. Now the question is that everything changing an AC voltage on primary to an AC voltage on secondary? Actually yes. The transformer changes the AC voltage on primary to another different AC voltage in the secondary. It may be higher or may be lower, and this is according to the number of turnings of both coils. This ratio between the AC voltage on primary to the AC voltage on the secondary is governed by the rule N divided N out, where N stands for the number of turnings, equals Vn divided V out, where V stands for the voltage. So as you can see, the transformer shown is a step-down transformer because it steps down the voltage. We can have a numerical value for more clarification. If we have a primary coil with 100 turns and a secondary coil with 25 turns in the transformer, if you feed this transformer from the primary coil with 200 volts of AC voltage as an input, the output on the secondary coil will be, by this rule, 50 volts. Interchanging the coil positions between the input and the output so the secondary coil have a greater number of turnings will give a step-up transformer. An important note is that the word step up or step down is meant by voltage. We have discussed the relationship between voltage and transformers. What about the current? To talk about current intensity and transformers, we must assume that our transformer is 100% efficient. For a 100% efficient transformer, the total power on input equals the total output power. If we apply the rules we studied in the electric current, we can change the form to the input current intensity multiplied by the input voltage equals the output current intensity multiplied by the output voltage, because power equals current I times voltage V. If we have a numerical example, we can find that if a step-up transformer has an input current of 100 amperes and an input voltage of 20 volts, if the voltage is increased from 20 volts on primary to 200 volts on the output, how much will be the output current? Applying the rules, the output current will be 10 amperes. You can easily notice from the results that if voltage is increased by a step-up transformer 10 times, the current is reduced by 10 times. But one important thing must be taken into account. The question must mention that the transformer is 100% efficient. Otherwise, the rule power input equals power output will not apply. A 100% transformer assumes things about the transformer. Number 1, the power input equals the power output. Number 2, no energy or power loss in the transformer itself. Number 3, the transformer does not heat up, so no energy is lost as heat. Also assumes that all magnetic field from primary reaches the secondary. Number 5, no eddy current. This is a type of current that may be generated in the coil and opposes the transfer of magnetic field from primary to secondary. The national grid is the network of transmission cables and other components that help delivering electricity to homes. Starting from a power station that generates electricity, there must be a step-up transformer to increase the voltage and decrease the current. In fact, we do not need the high voltage, but we really need the low current. This is to minimize the heating up of the wires and hence minimize the energy and power loss due to the resistance of the cables. Before factories and industrial areas, there must be a step-down transformer. This is to reduce the voltage and increase the current to values that are suitable for industrial uses. Also in populated areas, a step-down transformer is needed to reduce the voltage and increase the current to suitable values for home use. To connect between a power station and homes, we need cables so the electric energy produced by the power station can reach the consumers. But direct connection by cables as shown will make some problems. The power produced by the power station will not efficiently reach the consumer. A lot of electric power is lost in the connecting cables as heat. The power lost in cables as heat is given by P equals I square R. As you can see from the equations, two factors can affect the amount of power lost. Number 1, the resistance of the cables. Number 2, the current in the cables. If we minimize any one of these two factors, we can minimize the power loss. To reduce the resistance of the cables, this can be done by replacing the cables with thicker ones. But this solution is expensive, so we have to think about the other option: reducing the current. Using a step-up transformer after the power station and before the transmission cables. This will increase the voltage and decrease the current. So electricity is transmitted in cables with high voltage and low current. This will reduce the power loss due to the resistance of the cables. After transmission cables and before the end user, we need a step-down transformer to reduce the voltage and increase the current to suitable values for home use. This can be summarized as: number 1. A step-up transformer is added after power station and before transmission. It increases the voltage and decreases the current, so reduces the power loss I²R due to the resistance of the cables. Number 2. The step-down transformer is added after the transmission and before home use. It decreases the voltage and increases the current to suitable values for home use. Even the advantages are many, there still must be some disadvantages. Number 1. Difficulty of installation. Number 2. Contact may be lethal. Number 3. Overhead cables must be high above ground. Tall pylons are expensive. Number 4. Underground cables are very expensive and they are difficult to maintain. Number 5. The cost of transformers. In this lesson, Electromagnetic Induction, Part 2, Moving the Magnet, 3 parts. Number 1, Moving a Magnet. Number 2, Transformers and how they work. Number 3, how electricity is distributed by the national grid.